Okay, so this is our segment addition postulate. A postulate or axiom is a statement that is accepted as true without proof. It's so obvious that the math gurus decided we don't have to prove it. Self-evident. So, there's a couple of words that we need to unpack here. The first one is the word between. So, between means not just like, they couldn't be down here and be between. Okay, it has to be on the same line in between. Does that make sense? Okay. It's very specific. So it says, if point B is between point A and point C, then, well, let's think about it. If this was 3 and this was 6, what is this whole thing? 9. Okay? So that means that the length AB plus the length BC has to add up to the length AC. Yeah. Now, there's 2 F's in if. That's not a typo. Does anybody remember what this means? Good. Okay, now that, if you can't remember, is a biconditional statement. And what is special about that is that I can make conclusions going both directions. If I know that point B is between points A and C, I can say this. If I know that these two added together makes that sum, I know that B is between A and C. Okay, so it goes backwards and forwards. So let's write that real quick here in orange. So if AB plus BC equals AC, then B, I should say point B instead of good example. Point B is between points A and C. So I can use that biconditional statement to make conclusions going in either direction. Okay. Let's look at how we can use this for proof. Okay. So we know that point E is between D and F, the points. We have to find DF. We're going to have to find X first, and then we'll find DF. Okay? So if we're completing this first statement, we know that DE is 3x minus 1. What's EF? 13. And then we also know DF. 6x. And we know all of those things because they were given to us. How do we know that point E is on DF? Are we guessing or did they tell us? They told us. That was also given. Yes. Okay. So, if we know that a point is on a segment, what DE plus EF has to equal what? Yeah, good, DF. So, what tells us that? It wasn't given to us. It's a thing. It's a postulate. Which postulate? It's got a whole box. It's literally right where I'm pointing. What is that box called? Yeah, the segment addition postulate. Yes. I am so impressed. Now that I've got that set up, I have expressions that I know for DE, EF, and DF. They're right here. So it's the substitution property that allows me to replace DE with 3x minus 1. So DE is 3x minus 1. Okay, I've got a plus right here. EF is just 13. And then bring down my equals. My DF is 6x. So it's my substitution property that allows me to substitute those expressions for DE, EF, and DF. Good? Easy peasy? Now, back in Algebra 1, the next step you called combining like terms. Okay, the real fancy name for it is the substitution property, because you are substituting one expression for an equivalent one. So I know that negative 1 plus 13, an equivalent simplified expression, is just 12. That's the substitution property. Okay, so 3x plus 12 equals 6x. Substitution property. Now this should look very familiar. You did a million of these last year. How do we get 3x alone? Subtract 12 from both sides. Oops, no, okay, I said the wrong thing. We want the x's alone. I'm going to subtract 3x. So what we said wasn't wrong, but it wasn't helpful either. That would have just helped us go in circles. Okay, so we're subtracting 3x from both sides, and now I have 3x on the right and 12 on the left. So that was my which property of equality? Yep, subtraction property of equality. Okay. And now it should be a little bit more clear why your algebra teacher didn't let you abbreviate sub-prop. Because look. Okay? And they were like, just wait. Your geometry teacher is going to get mad at you. And this is why, because there are a lot of properties that will have similar names, so we got to know which ones we want. Okay? All right, now what? Okay, we're going to divide both sides by 3, and we get 4 equals x, and that is our division property of equality. Anyone's hand feel like it's going to fall off yet? Stretch. Okay, so we've got x. What are they asking us to find? DF. So DF is this whole thing. So I have to take my x and substitute it in again. So that'll be 6 times my x, which is 4. So my DF is 24. So if the whole thing is 24, and this bit is 13, what's DE? 11. Yeah, this part right here is 11, because it has to add up to 24. Actually, plugging in the x there to make sure that you get 11 is a good way to make sure that your x is right. You see how you can kind of check your work? So if I do 4 times 3 is 12, minus 1 is 11, and I get something that makes sense with the rest of my problem, I can feel pretty confident that at least my algebra was right. It always made me feel a little better. All right. Okay, point P is between points L and N. Okay, I already feel like I need to draw a picture. Drawing a picture is one of the most sophisticated mathematical tools in your toolkit. When you get to physics, the first thing you'll draw for every single problem is a free body diagram. And it's not because physicists are dummies. It's because that's what smart people do to solve problems. You understand what I'm saying? Like, draw a picture. All right, point L, N. Point P is somewhere in between. We don't know where. It doesn't have to be perfect. We are given that Pn, that's this bit, is 4 less than 6 times LP. Can we make LPx? Would that help us a little bit? Do we know what LP is? Okay, so if I make LPx, how do I write 4 less than 6 times x? Okay, I think you said it. 6 what? 6x. Good, good. 6x. We want 4 less than that. So would I add 4 or subtract 4? Okay. Okay, and we also know that the value of ln is 31. Well, that's the whole thing. Okay, we have to find x and pn. Any ideas?
X minus 4 equals 31.
6x minus 4 equals 31. Okay, you're warm. What are we missing?
X plus 6x.
Yeah, we have to add that with LP. So it's got to be the PN plus LP equals LN. So we need to put the plus X up there. It doesn't matter if you put it second or if you put it first. Addition is commutative. 2 plus 3 equals 3 plus 2. They both equal 5. Doesn't matter. Okay, so how many total x's do I have? 7. So when you were in algebra, we just called that combining like terms. Now we know that that is a substitution property. Okay, now what? Okay, so I get 7x equals 35, so x has to be 5. Am I done? What do I still have to find? Pn. Okay, that's this bit. So I'm going to substitute it back in. So I'm going to say Pn equals 6 times my x, which is 5, minus 4. And someone said it. 26. Okay. How do you feel? Okay. No one's crying. We're moving on. Okay, remember we said that the segment addition postulate had an if and only if. So it works forwards and backwards. If we have these lengths, we should be able to see if u is between points T and V. So what are we going to draw first because we're smart like physicists? Yeah, we're going to draw a picture. Okay, it doesn't have to be pretty, really. So we want to know if u is between T and V. So I'm going to put T and V on the ends and u somewhere in the middle. and then label everything and see if it makes sense. Okay, so they're saying TU is 8. UV is 11. And then TV is 17. What do you think? Okay. Why? Yeah. We know that 8 plus 11 does not equal 17. Okay, 8 was TU. 11 was UV. And that did not add up to TV. I'm just doing substitution backwards, right? So, by the segment addition postulate, point U is not between points T and B. Yeah.
Can you use the arrows?
Yeah. So if this side was supposed to be 17 and these sides are too long, do you see that it would make us a little cute triangle instead of a straight segment? They'd kind of bow out. Like instead of being collinear like this, it would be 8, 11, 17. Does that help your brain a little bit? It can't be between because 17 is too short. It would kind of bow out into a triangle. Okay? Yes?
These are coplanar, not coplanar.
They are coplanar, not collinear. Thank you. All right, we are going to do a construction. Compasses out, straight edges out. Get my own compass. Yeah. Whoa. Okay. So what properties did our perpendicular bisector have? Well, what kind of angle does it make with PQ? So it's going to make, oh my gosh, makes what kind of angle? Okay, right. With which segment? PQ. What does the perpendicular bisector do to PQ? Yes. Splits PQ into two congruent segments. We are also supposed to label the intersection point N. So we had your little, right, and then this was congruent to this, And then this should be point M. At M, point M, if you had to guess, what would you call point M if you were to give it a special name? If it's in the middle and it's a point?
Origin.
If you were in charge of naming it, if it's in the middle and it's a point. Yeah. No. Yeah, it's the midpoint. Point M is the midpoint. Okay, more on that later. Okay. So, the perpendicular bisector theorem says that if a point is on the perpendicular bisector of a segment, like point X, then it is equidistant from the endpoints of the segment. So, if I know that AB is getting chopped in half, and if I know that line L is perpendicular to segment AB, then I can say that AX is congruent to BX. Easy enough? Okay, this is where it gets dicey because I don't like how this textbook did this, but I want to talk about it. So let's redraw this picture. Okay, here's point A, here's point B, here's point X. What this is saying is if this and this are congruent, okay, this is right, but the picture is messed up. Says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So it is on this perpendicular bisector. Okay, however, without knowing that either this is a right angle or these two are congruent, okay, it could also be on here. Do you see what I'm saying? No. Okay, flip. We have to find the measure of TU. So, I have two pieces of information. I know that these two are congruent, and I know that that is a right angle. Therefore, UW is a perpendicular bisector. So I can conclude that UT has to be congruent to UV. Okay, I had to have this piece of information, and I had to have this piece of information to know the third thing. I need two for the third. One is not enough. Okay, so if I know those segments are congruent, what do I know about their measures? They're what? Yeah, they're equivalent. Those two measures are the same, so I can write a cute little equation. 7x minus 17 must be equal to 3x plus 9. Okay, go ahead and solve that. Okay, I got 6.5. Huh? What's 9 plus 17?
26.
Okay.
And then that's 6. That's just 6.
So am I done? What do I have to do with the 6.5? Plug it in, plug it in. Okay. So TU is that one, but it doesn't really matter because their measures should be equal anyway. So if I want to know if I got it right, I could plug it into both and see if I got the same thing, right? All right, let's do it. So I want 3 times 6.5. Put your calculators away. We're going to work in our brains today. I'm going to show you how to do this in your head. Okay, now, you guys all know the distributive property, right? Okay, I want you to rewrite this as 3 times 6 plus 0.5 plus 9. What is 3 times 6? 18. What is 3 times a half? Oh, now it turned into a problem that I can do without a calculator. Look at that. You guys can do 18 plus 9 plus 1.5. No problem. Because one of these days in Algebra 2, they're going to take away your calculator. You might as well practice without it, right? All right, what did you get? 28.5? Okay. Okay, so that was TU. Okay, you can test the other one on the calculator. Do 7 times 6.5 minus 17. See if you get 28.5. Did they give us units? No. Okay, given that L bisects DE at point G. Okay, what do we need? They didn't give me one, so what am I going to have to draw for myself? A picture. Okay, so I've got segment DE. Okay, I know that L bisects. Does it say that it's perpendicular? So it may or may not be. All I know is that it's going to chop it in half. Okay, so look for the halfway point. That's going to be G. And it's bisecting, but it may or may not be perpendicular. Okay, if you don't know, you don't know. Okay, we know that DG is x plus 3. And we know that DE, that's the big one, is 2 less than 6 times the value of x. 2 less than 6 times the value of x. If you need to go back to the one that we did on the front, go back and look at it. 2 less than 6 times. Who's got it? Yeah, 6x minus 2. Good. Okay, what do I know about this and this if DE is getting bisected? Yeah, the measures are equal. So if this one's x plus 3, so is that one. Okay? So we have to find x and DE. So think about your segment addition postulate. What plus what has to equal what? Set up your equation. Or how many of this x plus 3 do you have? So you can either do this plus this, or you can do 2 of it equals. Double it. Huh? Yeah, solve it. Go ahead. Okay, I'm going to show you a secret. Could I distribute this too? Yes, but then that just makes more work for me. Do you see that the 6 and the 2 are both even? Okay, I'm also allowed to divide away the 2. And it actually makes it fewer steps. Now I have x plus 3 equals 3x minus 1. Fewer steps, people. Now what? I can add 1 over and I get 4. Subtract the x and I get 2x. So what is x? 2. Okay, am I done? What am I finding? DE, I'm finding the length of segment DE, so I have to plug it in. So DE is 6x minus 2. So 6 times 2 minus 2. So basically 5 times 2, which is 10. Okay, does it tell us any units? No. So what's DG? Five. What's GE? 5. That's fun. You can plug them in and make sure they work, right? That's how you know you did it right. Okay. Okay, let's say, okay, we've already done a perpendicular bisector construction, so we're going to skip this one. If we need to do another one later, we'll come back to it. You ready? We're going to see if we can finish up for today. Okay, the midpoint. M of AB is the point that bisects our segment into 2 congruent segments. If M is the midpoint of AB, then AM is congruent to MB, and the length AM is equal to MB. So these are segments. These are lengths. Remember how much I ranted about the notation. This is important. Yes? Did I write the same thing? Not the same thing. Okay. So this is one of those things that we can also use backwards and forwards. If I know that AM is congruent to MB, and M is between A and B, then I can say that the segments are congruent using the definition of midpoint. Okay, flip. Okay, so you can see point D is the midpoint of EF. How do we know that? It's given. Okay, so that's one of our given statements. What else is given to us? Hello? Right? Okay, ED equals 4x plus 6 and DF equals 7x minus 9. So what does segment ED have to be congruent to? DF, segment DF. Don't forget the bar over it. Okay? It is the definition of midpoint that tells us that. So if I know that the segments are congruent, what do I know about their measures, their lengths? They are equal. Okay, that is the definition of congruent that tells us so. ED, no bar, has to be equal to DF with no bar. Okay, if only I had algebraic expressions for ED and DF. Oh wait, we do. It's our givens. Here's ED. Here's DF. What allows us to replace those? Starts with an S. Yes. Okay. Now what? Where do I want my X's? Okay, can we move them over there? Okay, so subtracting 4x from both sides gives me 3x minus 9 equals 6. What allows me to subtract 4x from both sides? Yep. Okay, now what? Add 9 to both sides. So that is our addition property of equality. Okay, now what? Divide by 3, so I get 5 is my x. That was division. I had a brain fart. I was thinking about something else. Okay, there's a property that we're going to learn about, and you're going to be like, why would we ever need this stupid property? And I'm going to show you now so that we can talk about it. So if I ever wanted to write the x first, like x equals 5, that is called the symmetric property, where an equation is true whether I write it backwards or forwards. Okay, that is our symmetric property. Okay. All right, now we have to find ED, DF, and EF. Can you guys do that at home? You just plug in? Okay. So I'm going to put you in charge of that.